Uh, we'll be continuing the linked binary tree and linked binary search tree. So I apologize if the quality so far hasn't been as good. I've tried to fix that, so we'll hope it's even better. So today we're going to continue with the linked binary tree. So I've already created a class called linked binary tree. So I'll just redo that. Public linked binary tree of generic type T. We're working with generics again. Excuse me. Then we'll say implements binary tree ADT. I think we just did that one. And we're going to implement something else, iterable, to work with the iterators. What's up with that? Strange. Link binary tree. Link binary tree, did I spell it wrong? Link binary tree.java. Let's refactor that. Rename it. Can't even see the, cause my screen's so big, for some reason, it doesn't show the options, the writing the font very big at all. So we'll just refactor it. Alright, it seems to work. I might just double check. Actually, that's fine. We'll just go with that for now. So we'll import. I have a feeling it might be not a JVA file, but we'll import java.util. Yeah, I think it's not a JV file. Let's just scrap the whole thing. For you, if it's working, that's good. I'll just remake it, just in case. So linked binary tree dot java. Alright, this one didn't delete. It's telling me I might have to actually go in my src folder to delete that. Alright, so public class link binary tree. We'll have of generic type T. Implements binary tree ADT of generic type T. And iterable of type T. I'm just going to say of type T now. We'll import java.util for the iterable capabilities. So import java.util.star. So we'll make it protected because we're going to use this as a class to extend. This the linked binary tree itself won't be instantiated, I believe. We could have just made this an abstract class, perhaps. We can go back and try that later, and if I forget, you can try that later as well. So we're going to have a binary tree node object reference variable here called root. It's an object reference. So what is an object reference variable? This kind of confused me before when I was learning. So an object reference variable is, if you don't know, it's an object class. So it's a class that we created, which is now being used as an object, which is binary tree. That's a class that we created. Sorry, node. Binary tree node is a class that we created, and now we're using them as object reference variables. So right now it's equal to null. So currently it just points to null. But later we're going to point it to an object, so that's why it's called an object reference variable. We point it to an object with the equal sign. Later on, we'll point it to something. Then it'll it's what its name is really saying. Then it's going to refer to an object. So hope that helps. So protected int mod count. There was a error in this code, I believe, because I took this from the textbook. I remember asking my professor, and she said that on a remove, you're supposed to increment the mod count, and in this book, I believe, in this chapter, it was decrementing it. So I think there's a mistake. This textbook has been notorious for mistakes, so maybe that happens in all textbooks, but not really. I don't see that many. But anyways, we'll create the constructor here. So we're gonna have a few constructors, maybe even 3. So here we'll say it creates an empty binary tree in some Java doc, and then here we'll say public link binary tree. We're gonna reference the class name for the constructor, and we'll set here root points to null. It already was null, but here we're just explicitly showing that. Here we'll have the next constructor. We'll say creates a binary tree with the specified element as its root. So this is a long class, I believe. So this might take us a while. So public linked binary tree again. So we're overloading these constructors. And here we're going to set root to point to a new binary tree node. So we're going to instantiate our binary tree node to an object. So here we named it, we created an object reference variable. We gave it a name of type binary tree node of type T, right? Now we're doing that, the 2-line instantiation instead of just, we could have just done it on 1 line obviously. But here we'll take root and we'll point it to a new binary tree node. That's instantiation because we're using the new keyword. Then here we'll pass in the element as the parameter. And that's gonna go into our constructor, so we can see that later. Or we can just have a look now. See how there's 2 constructors here? We could have had 3 as we said, or more. But this one takes 1 parameter, and this constructor takes 3 parameters. So in our method here, where's our class? That's not the one. In our class here, which constructor is it going to use? Right? We're instantiating a binary tree node. Are we going to use the one, okay, we're instantiating a binary tree node object. Is it going to use the, so we're going to instantiate a binary tree node object that takes 1 parameter. So which constructor are we going to use? Are we going to use the one that takes 3 parameters? Or are we going to use the one that takes 1 parameter? Which one do you think? Well, we're going to use the one that takes 1 parameter. So that's how it's going to select which constructor to use. So now we'll do the next constructor. It's going to take, I don't think we're going to use this one, but you can. So here we'll say it creates a binary tree with a specified element as its root and the given trees as its left child and right child. So this one takes a linked binary tree, which is what it says. It's a linked binary tree. It's a subtree in the left. So it's going to have a root node, a left child, and a right child. But I think we're going to set up the childs, the left and right child, or the left and right branch ourselves. So I don't think we're going to use this one. We might, but I don't think we will. But if you have problems with it, just walk through with the debugger if you want to try using this one and step in. So here, so element, so param element, the element that will become the root of the binary tree. Param right, the right subtree of this tree. So again, it doesn't call them, sorry, did I say right? Should have been left first. But it doesn't call them left and right child, it's just left and right. You can change it to child if you want, or branch, whatever. You could call them leaves too, but they probably won't be leaves forever, so that might not be the best name. Subtree, you could say left and right subtree. So here we'll say at param left, the left subtree of this tree. That's it. Then here we'll call our constructor again, reference the class name, takes a t element as parameter, and it takes a linked binary tree object reference variable named left. So basically its own object type. It's a little confusing, but we'll work with it. It's not that once we debug it, it'll be easy to understand. Whoops. So we'll do linked here, binary tree of type t, and we'll call it right. I don't think we'll use this one. We might. I don't remember if we do. I don't think so. So here we'll instantiate a new root object again. So it's a binary tree node object, sorry, named root. So root points to new binary tree node object, just like linear node of type t when we instantiate a list node. Here we're instantiating a root node. So of type t takes an element as parameter. Here we'll say root dot set left. Do we have set left? Yeah, okay, so we're going to use the set left to right set right now. So what's going to happen is we're going to reference the root here with the dot operator. We could have also said get root. Do we have a get root node? We had a get root somewhere. I thought we had a get root node. Anyways, we'll just do it this way. So if you don't have an object to use, you can just take the, you can say this dot root as well, but you can just take the root you want. So we're looking for the root, the global root for this tree, the global root variable. So every linked binary tree node has a binary tree root, a binary tree node object reference variable named root, and every root node, sorry, every binary, so let me say that again, sorry. So every binary tree node object, sorry, every linked binary tree object has a binary tree node named root. So a binary tree node has a t element, it holds a t element, and it also has a binary tree node left child and a binary tree node right child. Now every linked binary tree can have a subtree, a left subtree, and a right subtree. So here what we're going to say is, this one's kind of redundant, this constructor, maybe that's why we don't really use it, but we're just going to call the global root variable here. And we're going to say, we're going to access it with the dot operator, so root dot, what do we have here? We have a bunch of methods to use, and most of them we created, so we'll say root dot set left, so that's a binary tree node object. So what does set left do? It sets the the left. So every binary tree node again has a left and a right child. Or sorry, left. Yeah, left and a right child. Same thing. Left and right node, whatever. So you have one binary tree node. It has an element. Think of it like a little. We'll try to do a diagram. We might need to. So we have an element here at the top. Think of it like a little triangle. At the top you have an element, and on the left we have the left child, and on the right we have a right child. So it's just like a little triangle. And you can think of the root as the top, and a triangle with a little node inside, which is the element. So the top could be the root, the left can be the bottom left edge, they call it, can have a left child, and the right bottom edge can have a right child. So it's a little confusing, but here we're just going to say root.set left. And we're going to call the linked binary tree, which also has, so again, every linked binary tree has its own binary tree node root, which has a left and a right child. So here we'll just say root.set left, left.root. Like, we can set all this manually, you'll see. We don't really need this constructor. Then we'll just say root.set right. So place another, basically it's saying here, instantiate, and so what is this constructor doing? It's saying create a linked binary tree. Create a data structure for us. And it's going to be a linked binary tree data structure. So this is a big one. So then it's going to say, okay, take our global root object reference variable for this object and point it to a new binary tree node object. So instantiate the binary tree node object and name it root and pass in an element as a parameter. So okay, take a binary tree node, make it hold an element, and that's it. So now in our linked binary tree we have a root binary tree node. So in that binary tree node, what do we have? We have an element, as we said. So in that root, think of it is that we have a root at the top of a triangle, like I don't know what it's called, an equilateral, where all sides are the same. Then you take the top, which is a root. We'll call that root. In the middle it has an element, and to the left it has a left child, and to the right it has a right child. Right now those are all null. The root binary tree node has 3 fields: an element, a left child, and a right child, and we can say the top is itself. It's just the root. So the root is the top part, right? This is the top part. That's the top part of the triangle is a root. It has an element below it, and it's going to point to another binary. It's a link here. This is a link. This is the linked part. It's going to point to a left binary tree node and a right binary tree node. Well, what does a left binary tree node have? Well, a left binary tree node has its own element and its own left and right child, which are going to be null. And it's this root is going to have its own. So its right child is going to have its own element and left and right child. So I hope you get the idea. We'll try to do a diagram after. So after this line, after we've created a root, that's why a diagram might be useful. But we have a root node. We have a root node now, which is a binary tree node, which now has its left and right child set to null, and let's just say it's holding 5. So it's saying, okay, take the root, take its left child and set it to a new tree named left and point it to another root. So that's all it's doing. So it's just putting a tree and putting a subtree on the left and a subtree on the right. Well, what does a subtree have? A subtree has another root, and what does that root have? That root has its own element and its own left and right binary tree node object reference variable. So just, if you don't understand it, don't worry, we'll come back. I don't even think we're going to use this one. You'll see, it's easy. Explaining it might be hard, but once you can see how it works in the debugger, it'll be easy. So here we'll create the doc, so returns a reference to the element at the root. Returns a reference to the element at the root. So at return a reference to the specified target, and it throws empty collection exception if the tree is empty. So public T, it returns type T. Sorry, so this is not get root node. This is just like get element, except for getting the root element. So we're gonna say T, public T, which is type T because it could be anything, string, int, double, float, whatever character. So we'll say public T get root element. And we'll say throws empty collection exception. Empty collection exception. So here we'll say if root is equal to null. We're going to check if it's null. So is the root equal to null? If it is, we'll throw a new empty collection exception. Link binary search. Oops, not search. Link binary tree. And you can just return null if you want, whatever. You don't have to throw exceptions. It's up to you. So if root is equal to null, then throw the exception. So if root is not equal to null and we have a tree, at least a root, we have a node in our tree, then we'll say return root dot get element. So we're returning a get root element, and we're just calling a get element in our binary tree node. I think we have a method here called get element. So it's just a method in a method, right? We're just saying, okay, this is an accessor method or a getter. They call that in C, I think. So here we'll say public T get root element. So we're gonna get something. We're gonna access something. Throw the exception if root is null. Then if it's not null, right? That's basically we don't have to put an else here. If this condition is true, then it's gonna hit, and exception is gonna stop. Sorry, the exception process is gonna start, so it won't get to this line unless we put finally. But then here so if it's not null, if our root isn't null, then we're just gonna return root.getElement. So we're gonna say, okay, access our root global variable here at the top. Every linked binary tree has one root. So take the root. The root is the node. What is the root? So the root is the node at the top of the tree. It's the very first node. It's the start of our tree. So in this case, let's just pick a number. We're gonna have a 5, or okay, yeah, we're gonna have a 5 at the top of our tree, right? So we're gonna say return root.getElement. So this is gonna call our object that we instantiated in the constructors, or in the constructor. We're gonna access it with a dot operator, right? Because that's what we do in main. We instantiate an object and then we access its methods with the dot operator. Well, where is this object? It's in here, and its methods are in here in the binary tree node class. So we'll say, okay, return the element in this node. Public T get element returns element because every binary tree node has an element field. Right? Easy. So let me just get some water. Sorry. So after that, we'll do the get root node class. You can just call it get root. I think get root would have been easier to use personally, but maybe node could work. I've already written this code in and called it node. So here we'll just say returns a reference to the element at the root. So here we'll say at return a reference to the specified target. At throws empty collection exception if the tree is empty. So it throws an exception if the tree is empty. So here we're just going to say same thing, public t. Oh, whoops, sorry. I'm looking at the wrong class here. My mistake. So we've already done that one. So here we'll say returns a reference. Great, my keyboard changed to something else. Hopefully the video doesn't stop. Okay, so, well, whoops, it still didn't change. What's happening here? Okay, now it works. So here we'll say returns a reference to the node at the root. Then here we'll say return a reference to the specified node. So it just returns a reference to the specified node. I think really what it's doing is just going to return a memory location to the compiler. I don't think you can, if you print this, I think you might just get a memory location or a hash code. But we're going to be using this internally to move this. We're going to be using this a lot, this method, to just to move the nodes around. And we're going to be doing some traversals later. Traversals, and we're going to be doing rotations for degenerate trees, which are like unbalanced trees. So we'll get into that in the next part, or the third part of this video. So return a reference to the specified node. Here at throws empty collection exception. Spell it right. I think I did. So it throws empty collection exception if the tree is empty. If the tree is empty. So here we'll say protected binary tree node of type T. We'll call it get root node. You can call it get root if you want. We'll say throws empty collection exception. Empty collection exception. Protected because only methods that can, it's using a little bit of security. So only classes that extend this class can access it. I forgot the word, encapsulation. So using a little bit of encapsulation protection. There's another word for it, I think. So if root points to null, then we're going to throw the exception. Throw new empty collection exception. Linked binary tree. Return root. No, we don't need that. So all we're doing is just saying get root node. Okay, return the root. So just return that, which is an object reference. we're going to use a set root. We might use it. So public void set root takes a binary tree node of type T. Root or node. We'll say this dot root points to the root parameter. So this dot root global variable or global field points to this parameter here. It's underlined itself, so it has some IntelliSense or whatever. So now you can find any parameter that matches it, and the only one is here. So if we do this one, we should get the one at the top. Right there. Root, root, root. Is that underlined too? Yeah, so this one's they're all underlined, so you can see it's global. So that's helpful. Okay, so now we'll do the get left and get right, set left and set rights. We're going to be using those a lot in the trees. You can traverse them yourself from the root. You can just go get left, get right, get left, get right. That's what I did mostly for my own trees, I think. I didn't really like the traversals too much because sometimes I didn't want to get all the nodes. If you need to get all the nodes, there's a special way to do it using recursion. They taught us using recursion, but there's another way to do it, probably with loops. But anyways, this way you'll see it's not that hard. Well, doing them recursively and writing it out, it is. But it's okay. Just use a small tree to practice. So public void set root binary tree node root. This dot root points to root. Then here we'll have the next method. Whoops. Returns the left subtree of the root of this tree. At return a link to the left subtree of the tree. So this is a linked binary tree again. I think we're going to do an array tree, which just has a formula 2n plus 1 and 2n plus 2. The nodes are stored at certain points, so I'll show you. So returns a link to the left subtree of the tree. So public linked binary tree of generic type T. Get left. We'll call it get left. What are we going to do? So there's a few ways to do this one. I believe the way they did it was a little different. So here we'll just throw the exception. So if root is equal to null, then throw a new empty collection exception linked binary tree. So here we create an object reference variable, because instead we would have had to maybe cast it to a binary tree node to get the left child. But since we're trying to make it for a linked binary tree, then we're going to do something special here. Pretty sure we could have changed it, but we're just going to say linked binary tree of type T. We'll just say result points to new linked binary tree. Type T. No parameter. We'll say result dot root, so we're just going to call the root of this of the tree we just instantiated, and we'll point it to the global root dot get left. So it's a little tricky. Personally, we could have just did So we should have a get left method in here. Get left. So there we go, get left, returns the left child of this node. So root has its own. So what is a root, right? Root is a binary tree node. That's how we're accessing that method in that class, in this binary tree node class, get left. So here we're trying to access it through a linked binary tree, right? So linked binary tree. I don't even know if we actually use this one, because usually we just access the root to traverse, so we might not even use this one. You can do a print like God here if we use it. You could put like print. You could do like system.out.println God here in a string to see if you're using it. But it's a little silly because personally, like, we're gonna just be using the root to traverse, and we're not gonna call a linked binary tree object itself. So I don't even think we use this one. If we do, we'll talk about it more. So we have our get left, returns, now we'll do the get right, so returns the right subtree of the root of this tree. This implementation has its fallbacks, like it didn't have a count when we instantiate nodes. Instead they use recursion to like count it. It's kind of silly. But you could have just used, when we do our linked binary search tree, because we won't instantiate this, we're just going to extend it to use it for our heap node as well, or our heap. But basically it's just going to traverse with the binary tree nodes, I believe. These get lefts and get right methods. And the way it tracks count is just by using recursion, and then it creates a count for every node that it passes, so it's kind of dumb. It could have just said add element in linked binary search tree, just increment count by 1, obviously. It's redundant. It's just kind of like a waste of time. But that's okay. Maybe they just wanted to practice recursion. So here we'll just do returns the left subtree of the root of this tree. Or sorry, returns the right subtree. And we'll do right return. Sorry, not right. So return a link to the right subtree of the tree. So returns a link to the right subtree. So here we'll say public link binary tree of type T. We'll call it get right. And here we'll just say if root is equal to null. Then throw a new empty collection exception linked binary tree. We'll do the same thing here, create an object reference variable, point it to new linked binary tree. So we're going to instantiate a tree here. Then we're going to say, okay, take this tree, so take result.root, and point it to root.getRight. So we need an object reference variable to access it, right? So like if we can't just call root.getRight, because look, I guess we can. Yeah, so maybe it's just like, it's kind of like, when I tried this, I thought that didn't work. root.get right. Yeah, so I think that's what I might have did before. If I just confuse anyone, I apologize. I think this, because that's all it's doing, right? It's just calling this method. But the reason why they're setting this to, actually, I think it doesn't work. Cause look. I may be right on this. Cause look, we're gonna do result.root points to root.get right, and this is asking us to return something. So if we return result, and if we just take that out, this still work. Whoops. Return. Can we just return root.get right? Okay, and see, it is giving us an error. Yeah, I thought I did try this before. So it's asking us to return a binary tree node and not a linked binary tree. So we already have that method. So how are we going to access this? How are we going to access the right child of our binary tree? Well, can we just, we already have these methods, right? So that's why I don't really understand what they're doing here. Like, I understand what they're doing, but I won't understand the purpose. Again, I don't think we even use these methods. We can see what we use later on. But personally, just don't worry about it. So if I did double confuse anyone, it just doesn't work. We already have the method. We already have the binary tree node method for our getters or accessor methods. So we don't really need this one. So let's just go with it. And the reason why we create an object reference variable is because, whoops, let's give us some brackets here. Because we need to, if we're doing it this way, then as I just showed, it doesn't work with just returning the root.get right. We have to create an object reference variable of this type. So of linked binary tree of type T. We could have named it, just named it temp, and set it to new linked binary tree. We're saying okay, well that root, which is null, right? Because this tree is completely null. Take that null root and point it to the root that we're looking for. The global root, not the root of this tree. It's a little confusing. Hopefully you understand there's two roots in this case, because this tree has its own root. And our general tree that we started has its own root. So this is just a temp, and we're just using it to pass values. That's it. Maybe they're just showing us some tricks, but I don't think we use this one. So we'll say here, see if we use this class, or this method. So see if we use it, or just see if we use. You could maybe even name this something else to see if you use it, or do the system.out.println got here, whatever, or test, whatever. So we got get right and get left, other methods that we probably won't be using. There's no set right and set left. Guess not. You can create them if you want. You can do the same thing. Personally, I don't think we're going to need those. If we do, we can create them later. So here we'll just do the isEmpty method. So we've seen that one before. So returns true if this binary tree is empty, and false otherwise. So returns true because it returns a boolean, or yeah, returns a boolean, so returns true if this binary tree is empty, false otherwise. So public boolean is empty, So returns true if root is equal to null. Doing this should give an error. Returns true if root is equal to, I think that's what the double equal sign means is equal to. Or you can do if root is equal to null, return true if root is, or else. Either if it's not true, if it's not null, then it's not null, but you can just do if root is equal to null, return true. If root is not equal to null, return false. Or you can just do it in one line, as we've done before. So we'll just say, returns true if root is null. Returns true if root is null, therefore it is empty. Returns true if root is equal to null. So that's it, we've seen it before. This time we're checking. We usually do if count is less than or equal to 0, I believe. But there's no count here. As we said, there could be, right? You could definitely do a tree with count, why not? The recursive way, it's a little confusing and it's longer, it's harder, it takes more time, or it's more time consuming. But here we'll say the size method, we'll do the size method, so returns the integer size of this tree. At return the integer size of the tree. And this is what I'm saying. So they use a method here called numChildren, which we haven't done. We'll do it in a sec. So public int size, instead of just returning count, right? That's what we usually do. It returns root dot numChildren. All numChildren does is just count. So I don't know why they did this, but it just returns the numChildren plus 1. I think when I first did this, I was like, well, why is the size like this? Well, it's because they're counting internally. They're not creating a variable. They're creating a local count and then passing that through recursion. I don't know why they're doing that. So here we'll do get height. So we'll just return the height of this tree. Return the height of this tree. Public int get height. If I have time, I'll try to get notes for all these data structures. But hopefully you'll know what this stuff is. So height is root minus 1. We'll go through it. We'll try to get through it. Height of root. Is there there's a method that we haven't done. Yeah, we're about to do it right now. Right under this one. So returns the height of the specified node. Returns the height of the specified node. At param node, the node from which to calculate the height. At return the height of the tree. So it's this private method. So private int height takes a binary tree node of type T, takes a node, it will say int result point equals to 0. So it's going to say, okay, if node does not equal to null, so if the node that we're looking for the height, Oops, did I spell that wrong? Which. So if node is not equal to null, so we're going to use the math class here, so result points to result.max. I actually forgot what that does. Returns the max and min. I think max and min, but I forgot what the formula is. You can just test it out. So node.getLeft. So node.getLeft. So result points to math.max of height. So of parameter height, and then of parameter node.getLeft. 1, 2 brackets, comma, then height of, oh, so this is a recursive method again, node.getRight, 1, 2, 3 closing brackets plus 1. Then return result, sorry, after that, return result. I don't know if we go through this, I thought we do somewhere. It just gets the height, so we can call the method. You can go, if you want to practice recursion, you can go through it. I think I showed you in that one video. Hopefully I posted it by now. It's was it the comparator video? So we'll be posting those. I'll be posting some every week. So hopefully I've posted that already at this point. So then now we'll do the contains method. We're almost done, but we actually. We still have the not the traversals, the tree. Yeah, I guess they are traversals. So we got the iterator methods, which are used for the traversals. We'll have the private inner class, the tree iterator. And we just have a few more methods here. Do we already do num children? Contains, find node. I feel like I'm missing something here. Actually, no, we already have num children, right, in binary tree. Binary tree node. Yeah, we do have num children. Okay, so that's a recursive method. That's the one where what I meant, where they're just counting here 1 plus 1 plus 1 plus 1. They're just adding the children. We could have just created a variable to keep track of that. Excuse me. Falling asleep again. Been at it for an hour already. Almost an hour. So we have the height method. Then we'll have the contains method. So we'll have returns true if this tree contains no element that matches the specified. So returns true if this tree contains an element that matches the specified target element, and false otherwise. So at param target element, the element being sought in this tree. So we've seen this method before. We're just looking for a target element. So we have param target element, the element being sought in the tree, in this tree. So at returns true if the element is in this tree, false otherwise. Excuse me. So public boolean contains T target element. So T temp, we're going to create an empty object reference variable here of type T. Boolean found points to false. We're going to use a try and catch here. So an internal try catch in a method. So find. Did we do a find method yet? I don't think so. Apologize if you don't understand. Should have maybe done it in another order. So maybe we can just come back to that method. But great, it's like a triple combined method. So let's do these backwards, okay? So let's leave that here so I don't confuse anybody. Because I didn't like that too when I was learning. So we'll just take a new line here. So here we'll put some doc here, returns a reference to the specified target element if it is found in this binary tree at param target element, the element being sought in this tree or searched for, at param next the element to begin searching from. Whoops. Okay, so we're gonna call a support method here, private binary tree up type binary tree node type T. Call it so it returns a binary tree node of type T. Variable or object reference variable, so find node. So it takes parameter T target element. Then binary tree node of type T next. So private binary tree node method named find node takes a parameter T target element, so we're searching for a target element, and we're going to say the next element to begin searching from. So private binary tree node find node takes parameter T target element, and it searches from a next node. Don't worry if you're confused, we'll go through it if we need to. I don't even think we use this method, but if we do, we'll walk through it. So if next points to null, return null. If next dot get element dot equals target element, return next. So next is the element to begin searching from, so you could just search from the root, right? So it's, I guess it's like a search, but it's like a advanced search. It's like, okay, well, you can start searching from the middle of the tree if you want, or you could search from like the top right of the tree. So that's what it's doing basically. Perhaps I could have just called it node, like instead of next, because next kind of throws you off. It's like, okay, well, next means it points to the next link, but that's not what they're trying to use next for. They're trying to use next for the node you're going to start the search at, I think. So if next.getElement.equals target element, then return next. And here we'll create a temp variable, binary tree node of type T temp points to find node. So it's a recursive method again. To find node target element and next.getLeft. So that's what the next is going to be, next.getLeft. So it's going to start once it searches, and if it doesn't find it, then it's going to call itself again. So if temp is equal to null, then temp points to find node target element, and then it's going to pass the next is going to become the next.getRight. So I think it's going to search it's going to go all the way down the left, and if it doesn't find it, it's going to go back to the right. It's go all the way down to the right. Return temp. So this is a long method if you're going to write it out, and if you have a big tree. If you have 100 elements, you could be writing that thing for like days. So use the debugger, and don't use a big tree if you're really finding something. But if you are using a tree, then I guess these methods could become useful if you're really searching for something that you need. But practicing these methods, it's kind of a pain to practice these, especially if you have a lot of elements. Like these methods take a few hours to just run through one method. Unless you're like Superman or something. So returns a string. Here we'll say we'll do the toString, so returns a string representation. I did have a special toString, but this is the way they did it. I swear I had a special toString. Maybe it doesn't work, but it's okay. We'll come back and do that special toString for the decision tree example code. So returns a string representation of this binary tree showing the nodes in an in-order fashion. So this is the book way, I think. This is the way they do the toString, so they just say public string toString. You can override that if you want. So we're going to call array unordered. So array unordered list. Type T. We'll call it temp list. Points to new array unordered list. Unordered list of type T. I spell something wrong. Unordered. Unordered list. Array unordered list. What's happening with that? ARRAYUNORDERED. Okay. ED. So in order, we'll call in order, which we haven't even written yet. Oh yeah, we still have to go back and do those other methods. Okay, so let's come back. Let's come back. Like I said, this is a long class. So let us come back and work up to where we were. So contains. So find node and find. So we'll do the find. Find node we did. Now we'll do find. And I'll try to find that special iterator toString I made. Hopefully I have that somewhere. So it returns a reference to the specified target element if it is found in this binary tree. Throws an element not found exception. Sorry, my nose is a little stuffed today. If the specified target element is not found in the binary tree. So I param target element, the element being sought in this tree, I return a reference to the specified target at throws element not found exception if the element is not in the tree. So public T find takes T target element as a parameter, throws empty collection exception. So binary tree node of type T current points to find node target element root. I don't know why they did it this way. They could have just did it in one method. So if current is equal to null, throw the exception. And then return, so outside of all that. So outside of all that, we'll just return current.get element. Current.get element. So now we'll go back to this method that we originally started. So we'll say temp points to, what does temp point to? Temp points to temp. So temp points to find target element, find the parameter target element. Then found points to true. If not, we'll just catch exception. Exception. Element not found exception. Found points to false. Otherwise, return found. So if it doesn't hit the catch. That's it. We'll go back to our toString now. We're almost done. We just have the tree iterator to do. It's about a quarter left. I'm just curious to see where that extra toString went. I think that's in my other notes here, just having a look. Link binary tree. Alright, let me open that up. Excuse me. Alright, where's my toString? Here we go. Nope. Where did I put that? I had a toString, I swear I had a special toString somewhere. Okay, if I find it, I will do a special toString somewhere and just comment it out if we have to. So the way they did it was so they said create an array unordered list of type T, name it temp list, instantiate that. Okay, so it's calling an in-order traversal, which we haven't done. So it's just saying pass in root and temp list, and then return temp list.toString. It's calling an internal toString here, a list toString. Actually, we have a list toString. We've created one for this class, so that's what it's doing. You can override that. And then here we're just going to create an iterator. Returns an iterator over the elements in this tree using the iterator in order method at return and in order iterator over this binary tree. So public iterator of generic type T, iterator, so return iterator in order. That's a method we're going to create right now. I thought we had a inner class for this. Okay, we do, but not yet. So here we'll have, excuse me, so iterator in order. That's where we are, I think. So performs an in order traversal on this binary tree. Performs an in order traversal on this binary tree by calling an overloaded recursive method, a recursive in order method that starts with the root at return an in order iterator. So at returns an in order iterator over this binary tree. So binary tree has just 2 elements for each node. So public iterator or iterator in order. So returns an iterator of type T, and we named it iterator in order. Here we call our array unordered list of type T temp list, we'll call it. Points to new array unordered list. Here we're going to call it an order method. We're going to do that right below. So they did it this way. I'm sure there's other ways we could have done it, but we'll just return a new tree iterator, which we haven't done as well. So temp list.iterator. So we might just have to we might just come back to this again because we're doing all these methods that we don't have. So maybe we'll just comment it out. And we got like 8 of those to do, unfortunately, because each one has 2. They have its class that returns a method, and then it has an iterator that just returns a tree iterator. So I think it returns them as a list, right? It returns all the nodes in a list form. That's what's happening here. So it has to lay them out somehow, so it just lays them out as a list. Let's just do our private inner class here. So we'll say private, actually no, sorry, we'll say inner class to represent an iterator over the elements of this tree. Then here we'll say private class tree iterator implements iterator of type T. What's happening with this? Yeah, so it's telling us to implement the has next, add next methods.